Hey, welcome to this part two of cache invalidation and cache eviction. In the part one, we looked into TTL based eviction. This video, we will be looking into reference based eviction. So, as we can categorize the reference based eviction into broadly into these categories. One is LRU, LFU, FIFO, and random. LRU, everybody would have heard about the least recently used items which are getting affected, which are the candidates for getting affected. Least frequently used, many of you would not have heard about it, but that is also an eviction strategy. FIFO, what comes in first will get evicted first. That's first in, first out. Random removes random keys. It's not the most preferred strategy. Let's look into the in-depth of LRU, LFU, which is mostly used at many places. So, what is LRU? What is LFU? Recently used versus frequently used. The most recently accessed item need not be the most frequently accessed item. So what do I mean by this? For example, let us take a key with a person ID, and then the person data is getting cached, or the card is getting access is getting cached. The cache may have a reference hit at the 120, if the TTL is 120 and the 119th second or 118th second, or probably take it as 100 second, and that item will get a new lease for another 120 seconds. But the person might not be accessing the cached data much frequently. For example, there is another shopping cart which a person is trying to add and probably shop it and maybe trying to share the cart or something of that sort. But they may be working on it very actively. So that data is getting accessed much more frequently. For example, 4 times during the last 120 seconds. That is called frequently accessed. So in terms of expiry, what happens with the least recently used is the one which is not used for quite some time will get expired. So somebody has to access that item just before the lease expires, that the lease gets renewed. It's a very simple strategy. Frequency is there is a frequency counter. We will look into it in depth. Based on the number of times which is getting accessed along with the time based, the number of counters. Number of times means what I say, it is not the duration. The number of times the data is getting accessed within the duration determines which has to be expired. So we could be preferring, or we should be preferring LFU many cases, not just LRU. LRU is a very naive expiration, but it is very widely used, which is a no-brainer. We don't need to look too much into it. And there are many times that we would have been gone through implement LRU cache. How do we need to implement LRU cache by writing code? What people usually do is sort the items which are based on the time. Whatever is the oldest, probably that will go at the into the tail, or probably if it is in ascending order, the least frequently used item becomes the head, and the head gets removed in a linked list or so. This is how the default implementation looks like. We might need to sort uh, and insert or access frequently accessed item are getting moved towards the tail, and whatever is least frequently accessed, or the less frequently accessed item becomes the head, and we can keep removing it from the head. And that is what is the strategy. But while inserting, we need to perform the movement part as well. That is how the default implementation, implement a LRU cache. We might have seen this algorithm implementation in many coding sessions or coding problems as well, right? Um, so we will look into it why that's not how it works in the caching engines, and those implementation in the next upcoming slide. But that's the very naive implementation of it, right? LFU means it maintains a frequency counter as and when an item gets accessed. The number of times the item get accessed will have an increment counter, and the items which are mostly accessed will bubble up to the will bubble up to the top, and then probably what is least access may go into the tail if that is the descending way of sorting, and then we can either remove from the tail or head based on the sort order as well. That also could be used one of the this strategy, maybe this is how the implementation works. Probably the naive implementation should look like, and we can implement it like this way as well, right? Random don't do, because usually random eviction is not the right strategy. LRU is most widely used. Let's look into the depth of how LRU is implemented in many caching engines, because we just looked into, or we might have looked into how LRU works, right? That's not how LRU works, or is getting implemented in much of the caching engines. Many caching engines like Redis uses an approximation based algorithm to evict the least recently used items, right? It takes, so how does that approximation works, and why we need to do approximation rather than doing a big sorting? Assume like we take a key size of about the number of entries which are in the cache are about 10 GB to 15 GB, right? That many values, millions of billions of data is getting inserted into the cache. So what are the candidates to be removed? If we need to perform a very naive based implementation, we might have to go through a series of keys to find out what it has to be removed. And so many swap operations will become the bottleneck. We need to keep a huge memory for this process, and it might be taking little more time to implement that process. But if you take the approximation algorithm, it takes a few set of samples and it runs what are those keys which are potential candidates, or which could be the potential candidates for it to be deleted. It's a probabilistic algorithm, and it eliminates those keys. That's how the LRU is implemented in Redis. It is exactly not the way that we spoke, based on maintain a linked list and maintain a hash map is not how LRU is implemented, and that's how we have been taught, or been destined to think in many times how LRU works, but that's not how LRU works in many caching engines. They usually sample it, we considering the size of the data which is coming in, and it is more much more accurate as well, right? It's maybe there are times that there is a data which is not recently used may get evicted, but the probability is very less, and Redis has fixed or have done a lot of fine tuning in this algorithm. As of version 3 of the Redis, they say that is much more smoothened. So what we can do is the max memory sample is a parameter which is provided or exposed by Redis. We can tune it to 5, 7, 10. When we go into some higher numbers, we would be able to accurately remove, or the prediction logic becomes much more smoothened. So the way that we also have planned about how do we test the expiration, right? How do we try to model, do a test model, so that the less frequently used items are getting expired, and the most frequently used items are not getting expired, right? We need to model this testing strategy to ensure the correctness of the algorithm, and we need to consider this while we model, or while we use Redis caches as well. We might have gone into this situation, but because of our cache refresh strategies, if the item is not present, we will try to load it from the database. And for those remote cases, would not have came up in many of the use cases. But when it comes to highly transaction or OLTP systems which are operating at internet scale, which requires caching as an architecture, this is a metric to be observed. How many times a TTL has resulted in loading the data from the underlying database, and what is the time is an important metric for an architect to understand when the LRU is used, because LRU works on approximation in Redis and many caching engines as well. So we need to keep this metric very clearly, so that we would be able to take decisions based on the metrics. The exact implementation of LRU needs more memory, because the swapping and other things, considering the huge number of values which are coming in, that's not how the way we write code using linked list and hash map is not how LRU is implemented in Redis or in many caching algorithms as well. Let's move into the next step. What is least frequently used? Least frequently used, also we looked into the naive implementation, right? We can set up a counter and we keep incrementing the counter for every key that we access during that period of time, and when the counter, whichever counters has lesser value, if we sort it in ascending, that gets bubbled up and then they get removed, but it requires a bigger memory as well, right? Usually we would have been trying to use the key value, and the value would be a counter, right? So that's not how it works, but we here Redis uses an approximate counting algorithm, which is also used in hyperlog, which is called Morris counter. We might have heard about this algorithm. It uses less memory space to maintain large number of counting values. We will look into I'll put a separate video on how Morris counters works and how hyperlog works. But that's how. This is also an approximation. We don't need an exact implementation for counters. It is okay that some of the items which are accessed uh, 99 times, or some of the items which are accessed 100 times getting expired before the 99 items. It's not exactly viable to have to have the differentiation between 99 and 100. So we would prefer an approximation counting based algorithms to expire for LFU, and that is very much agreed as well, right? Any other use cases which doesn't fit in LIFO, whatever it is, any other items which are fitting in TTL based, are the candidates to be fit in for access based eviction as well. There is another eviction strategy which is called size based. Any items which are exceeding certain sizes can be removed from the cache because it requires a lot of time to and the capacity to reference it much faster. But that's not available in many of the caching engines, but we can also think of LIFO, FIFO are also the some of the caching strategies that that is provided, but usually we don't need to look into the in the depth. LRU is very similar, we can say. So whenever we think of caching engines, I just touched based on these cache eviction strategies in distributed caches. We usually tend to think in-memory caches are equal to hash tables, which should not be thought of, right? We should be very clear about in-memory caching engine is different from a hash table or a hash map. So what makes difference is the cache refresh strategies and the cache invalidation strategies are not built in hash table, and building that cache eviction and cache refreshing strategies is a very hard problem. That is what I want to put it. So many people will try to. I'm using in-memory cache, and many engineers I hear saying that I'm just using a hash map. So that anyhow, it access pattern is WAF1, right? So I just do a lookup. So instead of implementing an in-memory cache like Guava cache or whatever it is, I use a hash map, which is certainly providing WAF1 access. Why it is not? But the expiration, the evictions are not handled, which is very important, and that what drives the caching engine, right? So we should not be using hash map and in-memory caching engine as a replaceable thing, or simultaneously. So if we have to use cache, if you have to use in-memory cache, use an in-memory cache. If you have to use a distributed cache, use a distributed hash. Don't replace an in-memory hash with a hash map or something of that sort. With this, we are coming to the end of the caching and the cache eviction strategies. Thanks for your time. Until next video, this is Bala Subramanian.